Enolates, friends, are just nucleophiles. That's all they are. At some point in organic chemistry, you get to the enolates chapter. Sometimes the enolates chapter is historically confusing for students. They really have trouble with enolate reactions. They're this mystical, magical thing. They're in their own chapter, and somehow that makes them harder to comprehend or understand. I'm here to tell you that it doesn't have to be that way. I'm going to show you a very simple tool to help you with enolate reactions that will make them just as simple as any other reaction you've learned in this course. To start us on that journey, let's look back at some other reactions you've likely seen at different points in this course. The first is the Williamson ether synthesis. We start with some kind of alcohol and we make some kind of ether. How do we do that? First, we take the alcohol and we add some kind of base, typically something like sodium hydride in THF or some other strong base. Doesn't really matter what base we use as long as it's a strong enough base. That deprotonates the oxygen to make an O- charge. That makes a strong nucleophile. A negative charge on oxygen. That negative charge on oxygen can then attack some kind of electrophile to add carbons 5 and 6. We would need some kind of alkyl halide that has carbons 5 and 6 attached in order to finish the Williamson ether synthesis. Oxygen would attack carbon 5, displacing the bromine, forming our final product. Williamson ether synthesis, we deprotonate the oxygen to make an O- that attacks an alkyl halide to form the ether product. Similarly, in an alkyne alkylation reaction, we start with some kind of alkyne and we make a longer alkyne. How do we do this? We add some kind of base. The traditional base is NaNH2, sodium amide. That nitrogen on sodium amide deprotonates the alkyne to form an alkyne anion to make a intermediate with a lone pair negative charge on carbon. That negative charge can act as a nucleophile and attack some kind of alkyl halide that has the rest of the molecule attacked. Here, it would have to have carbons 3, 4, 5, and 6 attached. This would be the alkyl halide we would use in this synthesis to make this longer alkyne. The nucleophile on carbon can attack carbon 3, kicking out the leaving group, and that will form the final alkyne alkylation product. So what can we say about all of these types of reactions? We need a nucleophile to attack an alkyl halide to do an SN2 reaction, but our starting molecule is not a nucleophile. So in both cases, we did something to turn the starting material into a nucleophile. These are fairly straightforward representative examples from various points in the course. Hopefully you didn't have too much trouble with these. You've seen these reactions before, and you probably could tell me exactly what we were supposed to do. But I want to step back a little bit and generalize what just happened. If we can put some labels on what just happened, it'll make what comes next a little bit simpler. In both of these examples, we had some kind of nucleophile attack some kind of electrophile to form our final product. But in both cases, our starting material was not that nucleophile. We had to take that starting material and do something to it to turn it into that nucleophile that we needed so we could add the electrophile and continue completing the reaction. So let's just kind of make note of that for a second, because that's actually very important. It is not uncommon for reactions that need nucleophiles. It is not uncommon that sometimes you need to make that nucleophile first before you can use it in whatever reaction you're doing. So let's just put a pin in that. We'll come back to that in a second. Before we talk about enolates, let's look at one more example, the Grignard addition. When I want to do a Grignard addition and I'm starting with an alkyl halide, I need to turn the alkyl halide into a nucleophile so I can do the reaction that I want to do. The way we do that is we add elemental magnesium. The elemental magnesium turns the alkyl halide into the corresponding Grignard reagent. And once I've made that Grignard reagent, I can use it as a nucleophile in this reaction. Here, I need to add it to an electrophile. It looks like it's going to be a 2-carbon electrophile with a carbonyl. That would be an aldehyde containing carbons 4 and 5. The Grignard reagent acts as a nucleophile, attacks the carbonyl, kicks electrons up onto oxygen. When the electrons go up onto oxygen, we get an oxygen with a negative charge, and then we add some kind of acid source, H3O+ or something. The oxygen takes the hydrogen, gives the electrons back to oxygen, and that forms our final product. Now we're ready to start talking about enolates. When I have a carbonyl, the carbon next to the carbonyl is called the alpha carbon, and the hydrogen attached to the alpha carbon is relatively acidic. It has a pKa of around 20 or 25 or so, depending on exactly what type of carbonyl you're looking at. So it is more acidic than an alkyne, less acidic than an alcohol, right in the middle. So in the presence of a strong enough base, I can use the base to deprotonate this hydrogen and put electrons onto that carbon, forming the conjugate base of the alpha carbon. This negative charge intermediate is in resonance. It has a resonance contributor that puts the negative charge onto the oxygen atom, and this molecule, stabilized by resonance, is the enolate. This is the enolate intermediate. So notice what we just did. We took a molecule that's not a nucleophile and we added a base to add a negative charge, and we turned that molecule into a nucleophile, just like we did with an alcohol for the Williamson ether synthesis, just like we did with an alkyne for the alkyne alkylation, just like we did with the Grignard addition to make the Grignard reagent. All we did was turn something that's not a nucleophile into a nucleophile. You've done this dozens of times already in the Williamson ether synthesis, the alkyne alkylation, and the Grignard reaction. Now we're doing it with enolates. Here is the big point of this video. Listen carefully. Enolates, friends, are just nucleophiles. That's all they are. Enolates are just nucleophiles. There's nothing special about them. There's nothing unusual about them. We make them the same way we made the alkoxide and the alkyne anion, by deprotonating an acidic proton to make a nucleophile. Enolates are just nucleophiles. So if the enolate is just a nucleophile, then it can do the reactions that just nucleophiles do. If in the Williamson ether synthesis we make a nucleophile to do an SN2 reaction, then I should be able to make an enolate to do an SN2 reaction. It's a nucleophile. So if I add an alkyl halide to an enolate, the electrons collapse down, the carbon attacks the carbon, kicks out the bromine, and I can do an SN2 reaction to make a longer ketone, just like I do in the Williamson ether synthesis. This would be how we would use the enolate as a nucleophile. It's just a nucleophile. And when we use the enolate as just a nucleophile to do an SN2 reaction, we call this enolate alkylation. This is the enolate alkylation reaction. We add the alkyl halide as an electrophile to the enolate, which is just a nucleophile. Enolate alkylation. In the Grignard reaction, if I can make a nucleophile to add to a carbonyl, then an enolate, I should be able to make the enolate into a nucleophile to add to a carbonyl. And I can do exactly that. If I add an enolate to some kind of carbonyl, we'll call these carbons 8 and 9, then the enolate can be a nucleophile. The electrons collapse down from oxygen. Carbon 7 attacks the carbonyl, just like the Grignard did, and we get a new carbon-carbon bond formed between carbon 7 and carbon 8. And just like with the Grignard, if we then add some kind of acid quench, we can protonate the O- charge to make an OH, just like we did with the Grignard reaction. The enolate is just a nucleophile. It can do all the same things that nucleophiles do. When we have an enolate add to an aldehyde or a ketone to do this kind of addition reaction, we call this the aldol addition. Don't get confused by the weird name. It's just a nucleophile adding to a carbonyl, just like the Grignard did. It's just a nucleophile. We can even extrapolate this one step further to things you've also already seen. When we have a nucleophile, we can add a nucleophile to an acid derivative, and if you recall what happens then, the electrons go up onto oxygen, they collapse back down to kick out that leaving group to do a nucleophilic acyl substitution reaction. If an enolate is just a nucleophile, then it can do a nucleophilic acyl substitution reaction. The electrons can collapse down from oxygen, carbon 12 can attack the carbonyl, the electrons would go up onto oxygen, back down, and kick out the OMe group to form as our final product after acidic quench to form a nucleophilic acyl substitution product. When the enolate does a nucleophilic acyl substitution, which is something you've seen dozens of times, we call this reaction the Claisen reaction. There is nothing new, nothing unique, nothing different about these reactions. Enolates are just nucleophiles. Let me end this video by empathizing a little bit. There are some peculiarities with enolates that I understand can make things a little bit confusing. There are a couple of different bases that we can use to form an enolate, so we need to know a couple of different bases, whereas in the other reactions, there's pretty much one standard one that we use. When we do these addition reactions, we can change up how we quench the reaction, and that can give us slightly different products. Sometimes we do an aldol addition, sometimes we do an elimination, and that can be a little bit confusing, and that's okay too. We can understand that. That's fine. But don't get tangled up in all those nuances. Keep it simple. Remember your fundamental principles. Enolates are just nucleophiles. If you can remember that enolates are just nucleophiles, that will make the enolate chapter go so much smoother.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.